All right, I think we have most people filed in now, so we will begin. Thank you everyone for joining the University of Texas Energy Symposium hosted by the Energy Institute today for February 9th, 2021. I'm Kerry Keene, Assistant Director and Research Scientist at the Energy Institute. Before I introduce today's speaker, I will show what we have in store for next week's talk, February 16th. We will have Rayford Smith, who is the Director of Energy and Analytics at Google. Rayford has had a history of his career working within the electric industry proper for electric utilities, and he has now gone to Google to manage their energy management systems of their server farms and building operations, and he's going to tell us how they're using information and analytics to optimize that. But today, it's my pleasure to introduce Hao Zhu. She is Assistant Professor here at University of Texas at Austin in the Electrical and Computer Engineering Department. Title of her talk is Spatio-temporal Learning for Enhancing the Situational Awareness of Power Grids. So we're going to learn some details about how to measure what's going on in the grid and how to think about future investments and how to manage the issues of the future electric grid. So we have different operational paradigms, as she says here. We're going to learn about, she's going to tell us about inertia and the dynamics of the grid. So a lot of us perhaps simplistically think of the grid as sort of a static thing with not alternating current, but we're going to learn some details about electrical engineering today. So Hao Zhu's research focuses on developing these types of innovative algorithmic solutions for problems related to learning and optimization for future energy systems, including the grid. She's a recipient of the NSF Career Award and has been advisor for 3 best student papers in this area within working within the electrical engineering professional societies of IEEE, Power and Energy Society, and their long-range planning committee. So with that introduction, I will stop sharing and hand it over to Hao, and I will remind everyone that you were to submit questions via the Q&A feature. I've been told, Hao has indicated that she kind of has a 2-part talk, so there'll be some chances for questions in the middle of the talk and at the end of the talk, and we'll pause in the middle to see if you have questions. So please submit your questions throughout the talk, and I will now stop talking and hand it over to Professor Zhu. Hao, go ahead.
Yeah, thank you, Kerry. Thanks for the nice introduction. Good morning, good afternoon, everyone. Thank you for coming to my talk. Today, I'll be talking about how to use different type of temporal data to improve the situational awareness of power grids. And I would like to thank my collaborators and students and NSF for funding support. So just to get started, usually when we talk about the power grid, we think there are like differently 2 types of grids. One is the high voltage transmission grids that usually covers over a large geographic distance. And it is very important to understand or analyze the dynamic behavior of these high voltage meshed transmission grids. And on the other side, there is also what we call the distribution grid. So this usually is from the utility to your homes, to residential customers. And traditionally, there's been lack of observability or data available for this part of the grid. But now with more and more distributed energy resources integrated at the grid edge around this distribution grid, people have realized that there is a need to improve the situational awareness there as well. So with that, the main question I'm trying to address here is that how can we leverage this increasing volume of data, which has different spatial or temporal resolutions, and use that for special applications or important monitoring tasks in transmission or distribution systems. So that's why I was saying my talk is 2 parts. So the first part is going to be covering the high voltage transmission grid, and then we will move to the distribution grid. So, but then feel free to ask questions. I will also take a longer break halfway through the talk. Okay, so just a little bit about this new technology, measurement technology for wide area transmission grid. It's called Synchrophasor technology. Some of you may have heard about it. I know that many of you are not from electric engineering. So I'll just give a very quick introduction on what it is about. So these phasor measurement units, they are providing a special type of sensing for alternating or AC systems. So we know in alternating AC systems, the voltage are sinusoidal waveforms. So although at every location it's easier to measure the magnitude or the oscillation level of the sinusoids, but then without synchronization, we don't have the good reference angle. Therefore, we cannot measure quantities related to angle or the oscillation frequency, which is the frequency here. So thanks to the wide deployment of these technologies in the last decades, so there are thousands of them deployed with hundreds of billions investment for the North American power system. We have now the capability to measure these important electric quantities such as voltage, frequency, and angle. Okay, so what can we do with that? So I'm going to show you a video animation here. Okay, sorry, I have to change it to a pointer. So basically this video shows that a real event happened in 2008 due to a blackout at Florida. So on the left is the electric frequency captured by these PMU devices. And on the right is the contour plot of this frequency changing over 60 Hertz. So I'm gonna show it again. So what happens is that at the beginning, there is a substation going outage, and there is immediately power imbalance triggered in the system, which leads to this frequency goes up and down throughout the system. So in this in our transmission grid, we call this oscillation propagation. You can think of it as some kind of wave, like an earthquake wave, or some kind of other type of oscillations that can propagate from the source to all the whole interconnected system. So what I'm showing on the right is the instant interconnection. That's like the one of the three major interconnections of North America. So this is what we meant by like dynamic behavior of the system. Thanks to these synchronized frequency measurements, we can now see how the grid responds to these kind of initial disturbance or initial power balance, initial outage. So, but here comes the question. These events are very rare. As an electric engineer myself, I would hope that this event to be as rare as possible. So, because this poses a disturbance to the system. So we actually don't have a lot of recording for these actual events. So how can, in a typical day, it's like a sunny day, nothing happened. We just have some small perturbations. We don't have this large fluctuation. So here comes the question. Can I utilize this everyday nominal data to try to infer this behavior of the grid, dynamic behavior under a large disturbance? Okay, can I use the average uninteresting data to do it? Okay, so this uninteresting data, everyday data is also what I call the ambient synchrophasor data. Okay, so why is this a difficult problem? Let me just show you a sample of this everyday data. So everyday, when there's just a very nominal conditions, the grid balance very well. So the frequency goes around 60 Hertz, or is almost perfect at 60 Hertz with a very, very small deviation. As you can see, this is 0.04 Hertz. And this slowing deviation, this is not because of system dynamic. This is purely because of the instantaneous power imbalance. Okay, so we have to eliminate this slowing varying trend, which we call trend in this ambient data. With that, what we come here as this white noise. So after this filter, we can see this white noise type of signal. This is actually what captures the dynamic behavior of the grid. So it is almost like a thermal noise, like you cannot see much pattern in that. Okay, so this makes that the everyday data uninteresting, but what we are going to show is that it is useful for us to recover this large disturbance behavior. So the inspiration comes actually from earthquake waves. So in seismology, people have shown that using this everyday ambient data, which they call noise field in seismology, we would be able to also recover how an earthquake wave would propagate in the ground, in Earth's media. So this inspired us that to pursue the same idea for power grid. Although the physics of the Earth's media and power grid is quite different, therefore we will need to use a new type of analysis tool for that. So I just want to mention that this type of work, processing ambient data, is generally called a power system dynamic analysis. There are quite some work on that, but still there is no, we are the first trying to establish this recovery property using the ambient data. And the focus here, I'm gonna show it later, is that using cross correlation of this ambient data, we'll be able to recover how the grid would respond under a dynamic disturbance. Okay, so I know that it's getting a little bit mathematic on this slide, but I just want to share like what is the physics behind this kind of oscillations, because it's very fascinating to me when I first learned about them. So to understand how this oscillation happens, you can think of generators as masses and the transmission lines as springs. So this is like a typical spring system that you have seen in college physics. And that's the same kind of phenomena in the oscillation as well. So in power grid, all the generators, their position is actually defined by the angle, and then the derivative of angle or derivative position is acceleration, but in electric world is actually the frequency. So that's why the frequency is immediately related to the power balance. Okay, because this is coming from Newton's second law. So the momentum or the mass multiplied by the acceleration is due to the total power imbalance, including from like the local mechanic power input. This is your the mechanic power input here. And then this Pij is how much power flowing on the transmission lines to the rest of the system. So this is a very interesting example of a second order oscillation system. And then we can also consider it into a network and writing it into a linearized, by linearizing the power flow model, we come from a perfect second order oscillation system. Okay, and I also have some special definition of the ambient condition. Basically, what I assume to be the everyday uninteresting ambient condition is that the input to the system is like a white noise and it's uncorrelated across time. So at every time, this perturbation is from a small load or supply demand imbalance. So it's very small and it doesn't have like any effects for the next time. And this is a basic model that I'm using here. And these are very classical models for power system ambient data analysis. So based on that, here is the claim here. So what are we trying to recover? We're trying to recover, say, a hypothetic disturbance happens at the source location, say it's around here in Florida or Southeast American, US here. So we want to know that if there is an outage here, what would happen to the frequency at Northeast New England, okay, or in Midwest, okay? What we want to know how this hypothetic disturbance would affect the rest of the system. So this in electric engineering terminology is called impulse response, okay? When there is an impulse input, how it would affect the rest of connected system. Okay, just interesting fact that this disturbance won't affect Texas because ERCOT system is not connected synchronously to the Eastern interconnection because the high voltage DC line would not make the propagation come through. Okay, so that's what we're trying to recover, obtain this disturbance response. So we have shown analytically that if I have the measurements at these two locations, these noisy like measurements at these two locations, okay, the measurements as you've seen from this last slide here, okay, by cross-correlating them, we will be able to recover this impulse response of interest. So this is the main results that we have established. Okay, so I'm going to talk a little bit about cross-correlation. So cross-correlation is a very powerful tool to process two time series. It's trying to quantify the similarity between two time series. So you can see that here, these two blue and right curves, they look similar, right? They're both kind of like sinusoidal waves in a way, hidden by some additive noise, of course. However, they're not similar in a way that they're perfect aligned. So cross-correlation is to say that if I move, I keep one signal, say I keep the blue fixed, okay? If I move the right signal around the horizontal, the time horizon, okay, how similar the two signals look alike under this time shift? Okay, so the below figure here is exactly the cross-correlation of these two signals here. And you can see that with a time lag around, say, like 2-3 seconds here, okay, or then there's a peak location here, indicates that these two signals are mostly alike when they have a slightly time shift between them. Okay, so basically cross-correlation is to quantify the temporal similarity of two signals under various time shifting. So how is this relevant for quantifying the oscillation or the propagation behavior of waves in electric grid? So the propagation of oscillation is exactly like a shifting of the initial disturbance to different locations. So to understand how the initial disturbance would affect another location, we can use the actual response of these two locations and then shift them, shift one of them, and then we will be able to know that, okay, under what shift they look most alike. And that's why that this is can be used to recover this response, dynamic response of the system. Okay, so so far we talk about the response of frequency, which is like the 60 Hertz value that you have seen earlier. Okay, we also can quantify the response of angle. So as I just mentioned, like generator is similar to a mass. So the frequency is actually the acceleration, and then the position, is, the angle is the position. Therefore, angle is the integration of frequency. So it would come no surprise that if we are able to know how the frequency would respond, we will be able to similarly know how the angle at another location would respond. Okay, so how is the angle useful? It turns out that by the modeling of electric power high voltage grid, the angle difference is very much related to the line power flow. Okay, so the line power flow on any high voltage transmission line is proportional to the angle difference at the two end buses of this line. Okay, so therefore, if we are able to quantify how the angle would respond everywhere in the system, then we are also able to quantify how the power flow would respond everywhere in the system. So this is the third result, which is about the line power flow response. Similarly, all these approaches indicates that to find these responses, it suffices to just use the actual data, the noise-like data, and doing this cross-correlation technique. And with that, we're able to recover these responses. So yeah, just to bore you a little bit more. So why can we establish that? Is based on the fact that these oscillations are like sinusoidal. They're coming from like what we call the second order modes. So if we compare the response at two locations, we will be able to just quantify these similar components with the sinusoidal, and then there are some additional components that can be eliminated because they are too small. Okay, coming back to the big picture here, so what are we proposing? So we are proposing that in a wide area grid, we can obtain synchronized measurements of frequency, angle, or power at different locations. Okay, we don't need the actual model of the system. We only need this ambient noise-like data, okay, from the real phasor measurement units. Okay, so after the initial processing, which I briefly mentioned earlier, called detrending, is to get rid of this slow wiring trend, we will be able to find these noise-like signatures at these locations. Okay, so it can come from any type of frequency or angle data at the source location, or these three types of data at the target location. Okay, and just to remind you that the source location can be anywhere, and the target location can be anywhere in the grid as well. And we don't need the actual topology or the actual parameters or actual model of the grid. Okay, we only need to rely on the data. So after this detrending process, we do the cross correlation, quantify the temporal similarity of the two, and this is the output we're obtaining here. And this gives us how an input at the source location, or hypothetic input, hypothetic outage at the source location would affect on this target location's response. Okay, so this is very computationally efficient because cross correlation can be found very fast by frequency analysis, like a FFT. And there is a derivation step, but doesn't affect the computation time much, depending on the data types. Okay, so this is like the overall idea of this dynamic modeling, data-driven dynamic modeling method that we are proposing. Okay, so just to show you some like examples. Okay, so this is a famous test case that people use for understanding the dynamic behavior of power grid. Is a 3 generator system. So 1, 2, 3 here. Okay. And it used to be developed to represent actually the dynamics in the northwest part of US between like Washington, like Oregon, and the North California area. So it's a very simplified model, but it's very amenable to like numeric analysis. Okay, so we use this model, and then since we have the model, we have the ground truth, the actual system response, okay? And we're gonna compare this data-driven approach using ambient data that we just developed or proposed in the last slide, and see how our approach validates this recovery performance. Okay, so just a quick note that one of our assumptions requires that the power system, high voltage system, to be lossless. And this is pretty common because on average, the high voltage system power losses is between like 1 to 3%. So it's almost lossless. And that's thanks to the high voltage transmission, which effectively reduce current and then effectively reduce thermal losses. So this is almost true, but it's not perfectly true as reflected by that this matrix K here is not perfectly symmetric, but we will just show later that it doesn't affect our recovery claim anyhow. So this is for this 3-generator system. So what we are plotting here, each is a 3x3 block. So this is from the input at generator 1, assuming there is a disturbance or outage happening at generator 1. And then this is trying to see what is the frequency response at different generators. 1, 2, 3. Okay, so this is input 1, 2, 3, and this is the output or target 1, 2, 3. So this definitely looks like a typical frequency response. So if there is a disturbance or outage in generator 1, then the first response will be coming from the generator itself. Its frequency will drop immediately. Okay, so that's why the frequency response starts from like a scaling highest value and then oscillating to smaller values. And if the input is or the disturbance is happening in generator 1, then at other generators, they will slowly notice that there is an imbalance, and then they would slowly respond to that imbalance by increase from a 0 deviation to the peak value. So overall, all these frequency responses looks like oscillation, as you saw earlier in the animation. And what we are able to see here is that the ground truth, which is the right curve, is very well recovered by our data-based approach, either the blue one or the green one. So their differences is that the ambient data are generated slightly different, but then the processing results looks very well matched. So we're really encouraged by this response. And we have also shown that, for recovering like the angle oscillation. So this is the signature of how the angle would change when there is an input at or a disturbance at generator 2, how the angle of different generators would change as well. And we also have very good recovery performance. So as I mentioned, because we can recover angle well, that means we can also recover how the line flow on each transmission line changes due to this disturbance. And we are able to, again, validate the effectiveness of this cross-correlation approach. Okay, so these are the second part of the validation, which is we use a more realistic generator model that goes beyond the second order oscillation that I used to build my analysis on. But because by and large, the second order dynamics dominates the system response. So even though we are not able to show for this more complicated generator model, the equivalence holds, from simulation, we're able to validate that these oscillation can be well matched, especially like the peak timing is very well identified. Like the peak level slightly has some kind of mismatch due to this higher order dynamics. So actually it looks better in the angle response, and then in the power response or the line flow response is almost unnoticeable. So there's tons of validation we can do with different test systems, but then there's no better validation on using real data. So we were fortunate to get the real Eastern interconnection frequency data for 15 minutes. And we were going to compare that response to the 2008 event seen from the video. So this is the sample data that you've seen earlier. We did the trending to remove this slowly wiring trend, and then actual ambient data would just look like noise. But then the cross correlation is able to recover their propagation behavior. So yeah, from this video, we did some kind of visual engineering by looking at this plot, and then we are able to identify like the locations with a propagation time of 0.5 seconds or 1.0 seconds or 1.5 seconds. So it usually takes around like 2 to 3 seconds for the initial disturbance to go around the whole eastern interconnection. And that's why what we are plotting here is the actual, like the arrival time based on the videos that you saw earlier. So this is 1.0 second and this is 1.5 second, okay? And then this is further away from the source oscillation here in Florida. So this is what the recorded propagation time. And then we use the real data, which is for a different operating condition, but then we are still able to have a good match between this estimated propagation time. So basically we use the real data, we do cross correlation, and then we find the peak timing. And that's where we estimate, well, the propagation time would be. So overall, they're pretty consistent, like there is a mismatch error at 0.1 second. And this is because our data that we have is at 10 hertz per rates. So the resolution is around 0.1 second. So we did have good mismatch considering this resolution of the data. Okay, so here concludes the first part of my talk. So it's on using these fast samples of synchronized grid frequency and angle measurements, we are able to recover how outage or disturbance of the event that happened in anywhere in the interconnected system, how it would propagate to the rest of interconnection. It's totally, it's model free, but it's building upon the physics model of power grid. And we are able to establish under this simplified but realistic assumptions about the grid model, these two, the model-based approach is able to perfectly recover the ground truth dynamic response. So we have actively pursuing applications. One is to look at how it can help to recover missing data, and looking into also potentially replacing some sort of numeric solvers, because this approach is very computationally efficient, and also use this insight to better design the wide area control to stabilize the system. So I am done with the first part and happy to take some questions.
This is Carrie. So there's one question that's probably appropriate at this time. That's just someone asking. So I guess I'm just going to make a statement. I think what you're saying is the benefits of your approach are: two, you don't need an actual model of the grid layout, or that's one, and then two, it's computationally efficient, so you can calculate relatively quickly a grid response, I guess, if you will. So that's my takeaways from the first part. The question the person is asking is if you could clarify effectively how you kind of use the correlations of these different points to actually know how long it takes for a disturbance to go from one place to another. So this idea of correlation, I guess there was a time shift. Is the time shift of the interference pattern, if you will, is that directly related to the propagation time, or how do you know that?
Yeah, so so like if we have like this perfect data itself, like if this is the actual data, we can cross correlate it, then we know that, okay, if it first arrived at the right location, then it takes another 3 seconds to go to the blue location. We can visualize that. And this is also reflected by the peak here as well. So this is the intuition that why it could work. But for like the ambient data, it doesn't have this perfect like propagation pattern. It has to be recovered from this second order analysis. So like, yeah, underlying it, it has some sort of like small oscillations that propagates, but it's hidden by this fast noise-like behavior. So it's actually much harder to see that, and then we have to use the cross correlation to uncover it.
Okay, so I think that's good for now. There's another question, but I think it's better for your after your discussion of the distribution grid. So
cool.
Go ahead.
Yeah. Okay. So I will again try to maybe focus on the big ideas of the distribution grid side of monitoring. So I think all of us have witnessed like there are more and more what we call the distributed energy resources that are installed or owned by individual customers, but then they are integrated to the grid. Okay, so one type of them is electric vehicles, and one kind of event of interest is that what is the start time of electric vehicles? Okay, and if I have the perfect like minute level data, it's actually pretty easy to tell like the start time of electric vehicle. However, at utilities, the smart meter data are collected every 15 minutes. So this start event, EV event, is very likely hidden in this 15-minute smart meter data. So the other type is what we call the behind the meter solar photovoltaic generation. So if we, as customers, install the roof solar panels on the rooftop, the utilities do not have direct visibility of this solar generation output, but it is to their interest to estimate the total solar generation for design of like protection devices or protection systems. Okay, so basically how to isolate fault when some like grounding events happened or things like that. So so the goal here is that as there are more and more the DERs installed integrated to distribution grid, the utilities actually do not have the perfect tool to monitor them or directly measure them. So why is that the case? So this is just the architectural view here. So at every house, we do have smart meters, but it is like every 15 minutes. So it kind of smooths out a lot of these hidden fast change events in this within each house. Well, that's also for, I mean, the 15-minute resolution is for privacy purposes, but it does have this kind of effects of hiding some interesting events for like EVs or some other type of high loading appliances or DERs. And the other type of measurements utility have is at some what we call feeder level measurements or like a grid level measurements. So it's only at a few locations. And this is what they call the distribution PMU, which can also which is also this fast sample data that it can provide. However, because they're really costly, so there are just a very few of them for a feeder system. So here comes two types of data with different spatial and temporal diversity. So the this feeder level D-PMU data, there has very good resolution, but then they don't have good spatial diversity. While the smart meter data, it is installed almost at every house, but it doesn't have this good temporal resolution. So the question comes that how do we jointly utilize both types of data to improve our visibility on each individual load, especially the DERs behind the meter. So just to set a little bit up on the problem, so we can think of that the load profile, the ground truth load profile are in these two matrices, P and Q. And both of them has like the number of houses and arranged by a time index time slots. So P is the real power, is what utility charge you for. So the Q is the reactive power. I don't know how many of you have heard about reactive power. So it's not like it's the imaginary part of complex power, but it's not imaginary power. It quantifies, I mean, it's related to the power consumption, especially usually for motors or drives. But then, yeah, so in addition to balancing real power, it's also very important to balance reactive power in order to supply for the motors or drives or HVACs, for example. So we want to recover these two types of load matrices. And then the two types of data that I just mentioned, the smart meter data, it can be think of as a compression on the time domain. So you have a linear transformation from the right that compress the ground truth data into like slower 15-minute resolution. And the feeder level D-PMU data, it is actually a spatial compression. So you multiply a matrix from left that would compress, like it will aggregate all the houses PQ data together. Okay, so this is a severely underdetermined problem because for every n by t matrix here, I would have a high time compression by an order of 1/15, and the high spatial compression by an order of like usually from 100 houses down to only 1 PMU data. So this is severely underdetermined. So we are not able to just use this compressed data to recover this original PQ matrix. And what we are going to do is to introduce special characteristics of PQ to help this problem. So just on the side, this is related to in power systems, what we call the state estimation problem. But usually the literature so far has not considered this time dimension. They usually consider it as like a static problem. It doesn't utilize the temporal characteristics of the loads as we will see later on. So what kind of characteristics have we utilized? One is about the fact that the appliance activities or EV activities are very infrequent compared to the total time horizon. Okay, so this is the real load data obtained from Pecan Street. You can see that most of these large appliance activities happens very rarely. Actually, these bolded ones are like the EV events, the actual EV events. They happen very rarely. Even for other types of load, it is also like an infrequent on and off. So this means that the load changes very infrequently, and or equivalently that there are sparse changes on the load profile. Okay, so this is what we introduced as the first characteristics here. So it includes like EV models. It can also include like typical household appliance as well. So we say that P and Q are jointly sparse, meaning that if they change together. Okay, so just want to point out that HVAC definitely also satisfies this property, but it has some periodic activity as well, pattern as well, which would pose as a challenge for our recovery later on. So this is a sparse appliance activity. The other one is the temporal pattern, or this correlated behavior among different rooftop solars. So what we observe from the daytime data in the Pecan Street data port is that the behind meter solar output for all the houses are pretty similar because by and large, they depend on localized factors like solar irradiance or weather conditions. So it is expected that the solar output from different houses, they look similar, maybe different by some scaling difference, factors. So in terms of a matrix logan, it manifests in low rank component in P, okay? Basically, these correlated temporal patterns, if you list them into matrices, we're saying that every row is a scaled version of the other. Therefore, it becomes a rank 1 component, actually. So this is the second characteristics that we are utilizing. So based on these two characteristics, we can introduce special type of regularization terms. So one is the nuclear norm for a low rank component, and the other one is what we call the group lasso norm, group L1 norm for this joint sparse changes of the PQ profile. So using this regularization terms, we are able to fill in this severe underdetermined system issue. So we basically want to find the PQ, which consists of low rank solar induced component and this sparse change resultant PQ change components. Okay, so that's how we are able to tackle this lack of observability issue in distribution or in monitoring grid edge resources. So what can we do without these recovery results? So one thing is that if, say that using the recovery, this method, we are able to find a better description of the load changes. So as you can see here, the actual data perfectly captures this EV events, and then the smart meter data does not perfectly capture it. But if we are able to recover this actual event signature, then we can first be able to identify an EV event at a residential load or residential home. So we have done that, use the recovery results for EV event identification, and by locating these change events in the recovered real power profile. So the other one is to do behind meter solar recovery. So from, as I mentioned earlier, the low rank component has the solar temporal profile. So using this recovered solar temporal profile, we are able to scale it and then disaggregate the total measurements to see how much of the total power demand is from solar. Okay, so I'm going to show you the results very soon. So we have tested this method in some realistic feeder systems with a small one with 30 houses and another one with 100 houses. Half of them has PV solars panels, and we consider the real data from the Pecan Street data port, and then we have generated the measurement data using this GridLab D simulation tool, and then add some small additive noise to make them more like measurements, not an actual value. Okay, so this is a show of this small feeder system. So we consider the feeder level measurements potentially at these 4 locations. And so we show first like the recovery for EV events. So this is the illustration of one of the events that we are able to recover perfectly the start time. So to quantify how much better we are doing now, we plot this called receiving operating characteristics. So for any kind of detection problem, we can essentially like vary the detection threshold. Therefore, you can see more and more actual events, but then it will have the trouble that if some of them may be false alarms. So there is a good balance of this what's called true positive rates and then the false positive rates by varying this threshold, detection threshold. So
How can I ask a question? Just clarifying for someone online, an EV event, is this an electric vehicle charging or it means something else?
Yes, it's EV charging or start or end events of the charging episode. Yeah, thank you for the question.
Yeah, go ahead.
So yeah, so to quantify this identification performance, we have to vary this threshold, and by varying the threshold, we're able to have a trade-off between the true positive rate and then the false positive rate. Okay, so this axis means an actual event being correctly identified, and then this horizontal axis meaning that no event, but decline, the algorithm decline, there's an event or like a false alarm. Okay, so ideally we want the curve to be as close to this top left corner as possible. So we're plotting here is by varying the number of feeder level measurements, how this performance improves as a result of more and more feeder level measurements. So when there's no feeder level measurements using smart meter data, because of this issue of time averaging, the performance is very poor. So we can only identify like 10% of EV events. But then just using like one feeder level measurements, we can kind of increase that to almost like 90%. And then with, of course, the more the merrier, and that's shown with this increasing trend of the curves here. So I also want to point out, because the EV loading is very large, so usually like the false alarm rarely happens, because yeah, it has to show a very large jump or drop of the load profile that we can be misguided to say that this is an EV event, but in fact it is not. Okay, so this is the results for the small system, and then for the larger system, we have the same observation. Although like the performance improvements is a little bit lower with one, because we have now 100 houses. Locating the exact event within for like 100 houses is not that easy. So that's why with like one like feeder level measurements, we can only have like 70% of recovery. So we also tested for summer data. So here comes the part with the HVAC events, HVAC activities. So HVAC has a periodic appliances. So they are kind of like sparse changes, but somehow because of this periodicity, they're also present in the low rank component. And this while is kind of the assumption that we have for the recovery. And we, first of all, we witnessed that we are not very well to capture the exact profile of the HVAC events. Sometimes it's not perfectly capturing like the up and down of HVACs, but by and large, we can still capture or recover this large EV start and ending episode. And the same ROC curve shows that, yes, by using the feeder level of D-PMU data, we can significantly improve the identification rates. But then compared to the winter results, this success rate has decreased as a result due to this presence of HVAC activities. So the second application is the behind meter solar estimation, as I mentioned. So it's very interesting here, like if we have directly the solar measurements output, you can see that they all look alike. So this allows us to use the low rank component in my recovery algorithm, identify what is the recovered temporal pattern from it. And it actually matches really well, even this fast transient of the solar pattern here. And using this recovered pattern, I fit in a scale version of this recovered pattern into this aggregated data. So this aggregated power data is provided by like the feeder level measurements. Okay, and I try to fit this one with this pattern here, and I will be able to well recover this actual total solar generation. So in a way, with the solar irradiance pattern here, I will be able to well estimate how much total solar capacity is, solar power is generated by all the rooftop solars in the feeder system. So this is very interesting to me. And again, coming to summer data. So the summer data has slightly like lack of coloration, but it's still pretty much look at the same parabola shape. So one thing that happens with our recovered data is that it, on top of this parabola shape, it also has some small oscillation, and that's exactly due to the HVAC events I mentioned earlier. The HVAC, the periodic HVAC events is also somehow low rank. So I have this oscillation at 15 minutes interval on top of this solar trend. So it's unfortunate, but I know that if I want to really get rid of it, I can do some bandpass filter to get rid of that. But I just want to show you the result to point out what could be potential issues of the recovery so far. Again, using this solar trend, the recovered solar trend, I can also estimate the total PV output from this aggregated data here. Okay, so this is the main part on the grid edge monitoring. So the interesting aspect to me is that we have different types of heterogeneous types of data of different resolution and different spatial diversity. And by jointly utilizing their respective strengths, we are able to say a lot of more about the DRs behind the meter PVs. And I think this is very useful if we want to better understand what is the status of the DRs at grid edges, at the grid edge. Okay, so with that, I would like to conclude my talk and take 4 questions.
Okay, thank you for this sort of tour de force of, on the edge of electrical engineering. So thank you very much. Got a couple questions here that are relevant. One I was kind of thinking of and somebody else asked is either, I guess, think about both the transmission level and the distribution level. What type of density of measurements are needed in order to employ your approach? I guess maybe particular for the transmission line and cross correlations. I noticed from your figure, I think ERCOT seemed to be not having as many measurement locations as the other grids. So, how many measurements do you need?
I think ERCOT has hundreds of measurements also, from what I heard.
Okay.
Yeah. So for implementing this particular algorithm so far, actually, I only need 2. I only need 2 meters because I only need to. So from that, I know how it goes from one location to the other. I only need to pick the 2 data streams from these respective locations. But if I want to know how it happens for this whole eastern interconnection, then the more the merrier. So usually we say that this behavior changes like 500 miles per second. So maybe like a radius of 500 miles is, or even lower than that. The coverage in that order is good. Yeah. So like usually, so far, like I said earlier, like there are like thousands of PMUs in the system. I think this is already pretty sufficient for my algorithm. Yeah. Okay,
so you're sort of correlating the time to propagate, and there's some rules of thumb for that. But I guess you're also correlating the magnitude of the propagation. So in your example, there was a blackout in Florida, but I guess there was not a blackout across the whole eastern grid. So is there something you can say about how you understand how far a blackout itself would propagate?
Yeah, so the blackout propagation, that's a very interesting, it's also an active research area, like cascading outage effects in power grid. I'm very personally interested in that, and I'm also trying to look into that as well. So that has to do also with like the protection devices. So if like the frequency deviation is not too much, then we believe that the grid has the capability to eventually go back to steady state, or somehow it's like if an earthquake is not too big, then we're having some transient phenomenon, but we don't need to worry, like eventually it will be damped out. But then what is worrisome is like in the meantime, there may be some other like triggering events, especially if that couples with some like transmission lines go out of service, or some transmission lines have stability issue, local issue, and then they being disconnected from the system. And that kind of triggering events is more worrisome because it will lead to like power redistribution to other transmission lines and leading to overheating. And that's what triggered to the 2003 blackout, and also part of the reason of the 2009 or 2011 San Diego blackout as well. So usually to trigger this large scale like cascading failure, is usually because we are lacking like transmission capacity as well due to transmission lines being out of service. So this frequency behavior, they would be coupled with this line out of service, and they can trigger a large blackout.
Okay, so somewhat related here, maybe I'm not going to try to guess the answer. So one of the questions was, if you have a large disturbance, would your correlations, if the correlations of the grid points between 2 points be significantly different than if you have a very small disturbance, and because you're measuring your correlations based upon essentially a normal operating condition? Does that matter? Maybe it doesn't matter because there's only small deviations in frequency that cause big ramifications, but you can tell me.
That's a great question. So we have different models to describe the grid behavior to different level. So what I can say is that initial response of this dynamic behavior is pretty much the same as the small response, the small signal response. But if we look at this recovery phase, like how much the frequency can go back to normal, that has other kind of mechanisms like control mechanisms, or like area-based control mechanisms. So it's not fully described by this small signal analysis. So there is some kind of mismatch if we want to understand what is like the longer term behavior, like 10 seconds after the events. But then for the first few seconds, this small signal analysis is quite adequate. Yeah.
Okay, thank you. There's one question here, just a question on the Florida blackout that you showed. Do you know how big? I think you said it was a generator that went off that caused the blackout, or do you know how much that was in relation?
So usually for an event like that, it has to be in the order of hundreds of megawatts.
So that one was.
It's probably
hundreds of megawatts.
I don't have the exact number, but maybe at least maybe even 1,000 megawatts, I would say. Yeah.
So
like is it for ERCOT, is our peak loading is 72 gigawatts. So like losing 1% may be a very big number. Yeah. Right.
So in the context of avoiding blackouts due to, let's just say, a power plant going out, I guess, more time of propagation, I guess, is good. There's more time for safety protocols or automatic systems to react. And so are you studying how that, say you have the map here showing these propagation times, how those would change as we change the generators on the grid, say to more solar and wind measurements? How do you think about that?
Yeah, so that could be possible. So that's why I was thinking also using that to look into some control design. So the generator, this slowing variation of generation capacity or shifting from fossil fuel-based generation to renewable-based generation would have effects on this dynamic behavior. But then what is, for this short time scale problem, there are also a lot of like effective control strategies, like a wide area stabilizing control, or even like local frequency control. So we can use this kind of method, this data-driven method, say that I want to change some control parameter setting and see how it would affect these short-term propagation effects. So that would be very helpful for designing like a immediate fast control actions.
Right. Okay. Thanks. So maybe there's another question here. Maybe we'll end on this. There was a question about the distribution grid, but I think you addressed that in your talk. You're essentially having to make up a lot more information for the distribution grid to estimate what's happening, just because there's a lack of data compared to the transmission level.
perhaps.
But there's a person here asking for sort of the electrical engineering 101 question again of reiterating, how we know or how you think about, angle and frequency like a mass spring system. So,
Yeah, I think that's the physics of the grid. So it is what makes interconnection preferred, because we can utilize the inertial resources for all the interconnected generators. So that's why at the beginning of electrification, we like more and more systems interconnected together, more and more generators interconnected together. But then this interconnection brings down the cost, makes the system more reliable, but also could lead to some resilience concerns. So if there is a local failure, it means that because of this interconnection, it would affect other places as well. So I think going forward, there needs to be a good balance between this interconnected grid to have cheap, efficient, and carbon-free generation from anywhere in the system. But at the same time, there is also a need to have local flexibility, like a local load response program. So this is already happening with what we call different type of grade forming or grade forming inverter resources. So allowing for some local flexibility or local response, we can also improve this resiliency when there is a wide area blackout.
Right. I think I will. I'll use my engineering skills here to try to answer this question on why the generators, or we might think of them as a mass spring system on the grid. So to this person, there are different types of energy domains at which we might quantify the amount of kinetic energy or amount of potential energy that exists. And we maybe normally think of linear mechanical systems, so linear force and a spring pulling on a linear spring, which I'll point it out. But in the electrical domain, we would think of the charge as potential energy, the charge that's stored in a battery, or capacitors, are essentially play the same role as a spring when you're modeling energy transfers. So capacitors play the same role as a spring. Inductors in electrical energy domain play the same role as a mass in the physical domain. So you're basically equating the transfer of energy from potential to kinetic energy, and there's an equivalent element, if you will, in each energy domain, whether that's magnetics, electrical, or mechanical devices. And so the mass spring, more people are familiar with rather than inductors and capacitors. So I think that's why I use that.
Yeah, sorry, I missed the question was on the.
I didn't state it well. I didn't state the question well.
Yeah, I thought it's like an implication of that. But yeah, generators are rotating masses. That's how we view them. Yeah, and we want more and more renewable resources to be able to either mimic or even go beyond the current generators in this kind of inertial support.
Right. So we'll leave it there. Apologies for not asking the question directly.
Oh, no.
And
I think I misunderstood it.
Yeah. So thank you very much. This is very interesting, and certainly I definitely do think at the edge of knowledge work here, at the edge of electrical engineering and understanding, how disturbances and how to monitor the grid, as it's just going to get more complicated, as you say, with more photovoltaics, more electric vehicles, and more renewables. It just gets harder to track what's going on in the grid. So your work is certainly at the cutting edge. Thank you very much, Haozu. So thank you for coming, and that concludes our talk today.
Yeah, my pleasure. Thanks.